So it's a pointer ownership model for C. It's inspired by Rust. David Svoboda and his colleagues at Carnegie Mellon Software Engineering Institute. David's going to give the talk. I'm going to give you a ping around 7 minutes before the end of the talk, so that's like to wind up.
So, okay. And that goes on the belt. Okay, so I think I'm mic'd up. Good. All right, so I'm here to talk to you about pointer ownership model for C inspired by Rust. So I'm going to start off with a little personal anecdote. When I was a student, I first learned about formal models, and I thought they're interesting academically, but they're tedious and expensive, and well, they take a lot of effort to do. So they're not going to escape out of the ivory tower. They're always going to be locked in academia. 5 years later, I learned about neural nets and came to the same conclusion. They're not going to escape out of academia. And well, in my defense, I was right for several decades. It's only been in the past 5-10 years that neural nets and large language models have become popular. And the fundamental question I have, which I don't have an answer to, but the notion is, can we use large language models to help us build formal methods and make formal methods more accessible and usable? So with that, I'll start the actual presentation. So of course, C programs are not memory safe, and we're going to focus in this project on temporal memory safety. So we're ignoring things like buffer overflows. We're instead focusing on things like use after free and double free. So the argument is that we are providing a model of managing pointer ownerships, lifetimes. It's inspired by Rust, and it's inspired a little bit by C++'s Ray. And it's inspired by the discipline that every C programmer who's ever had a memory error in their program and spent hours debugging it, as I had, in my student days, they quickly have to develop something like this. So we have a model. It covers lifetimes, much like Rust. The model helps reduce the problem of proving temporal memory safety to a satisfiability problem. So it can be done statically without having to actually run your program. As you might guess, building what we call a P model, that's the model applied to a specific program, building a P model can be tedious and long because you have to represent every pointer, but LLMs can help reduce the tedium and make it cheaper. And finally, we actually have test results. We ran this on 4,000 cases from the Juliet test suite. So I'll start off with an example of code. For my students, I like to ask, what's wrong with this code, and let them figure things out. For here, I'll simply point out what you can see pretty quickly, which is that the memory from error message is freed by line 15 by the usage function, and it's freed again by line 16, resulting in a double free. So this program is not temporally memory safe. So the problem is, in order to do that, you have to look at the code for both functions. We call that whole program analysis, and whole program analysis is it's workable in small examples like this, but it does not scale to real-world code that has more than 2 functions. So the idea is that we construct a P model for each function, which is what we've done here. And doing that, you can look at the P model and each function individually. So when you're analyzing main, you can ignore the code base for usage and just look at the P model and determine that error message becomes a zombie in line 15, meaning it points to freed memory, and it's freed again on line 16. So in other words, we don't have to run this program to see that it's not actually memory safe. So the main crux of the model hinges on responsible versus irresponsible pointers. For you Rust experts out there, they correspond to box pointers and references in Rust. And so we're basically trying to apply the same model that Rust's borrow checker has and apply to C. So responsible pointers are pointers that point to chunks of memory on the heap, and when the responsible pointer goes away, the heap memory should also be freed. In particular, each heap object should be referenced by exactly one responsible pointer. And therefore, that handles the aliasing problem. If we have a responsible pointer, we know that no other pointer can be dereferenced that points to it. So that way we safely manage heap safety. Irresponsible pointers are like reference pointers, or the blue ones in this diagram, and they can point to anything. They cannot participate in memory management, and the main concern with them is that they might point to something that eventually gets freed. So, for example, if this chunk of memory gets freed, then we need to make sure that the pointer to it never gets dereferenced. That would be a use after free error. I'm not going to go over these other threes, except for diligent pointers, because diligent pointers are kind of the boring, read-only things that we'll see those a little bit in later on. And fortunately, most pointers are diligent; they don't participate in memory management. Okay, so this is what we wound up building, a combination of a builder and, this whole thing on the left is what we call a verifier. So the builder, of course, constructs P models, and in our case, it uses a large language model. In our case, we used GPT-04 Mini, but you could theoretically use any large language model today, or you can build P models by hand. The rest of this is what we call a verifier, and it either says, the constraints you have are satisfiable or they're not satisfiable. We're using a stat solver, and so if they're not satisfiable, you get an unsat core. And at the base of it, an unsat core is effectively a Boolean proposition. It's kind of a proof that things are not satisfiable in conjunctive normal form. So it will be something like A and B and C and not A, which is contradictory. So when we first built this, we kind of assumed that people would use the builder and the stat solver together, and the constraint generator that feeds constraints to the stat solver would pull constraints from the builder's P model, and it would infer some constraints from the LLVMIR, which is derived from the source code by Clang. We actually realized that there's a second subset here where you can dispense with the P model. That's why the P model line is dotted, and you just infer constraints from the constraint generator, or from the LLVMIR. We call that the whole program stat solver because it simply answers the question, does there exist a P model that can satisfy this code or not? Is the code internally consistent or not? So that turned out to be useful for testing. It doesn't tell us what the P model actually is, it just tells us whether or not there exists one or none. So we wound up using that for testing. You'll see in the testing slides in a little bit. We expect that most people will want to use the builder and the LLM to construct P models. P models are actually good for representing the intentions of the programmer, and they're good to maintain as the program evolves. If a P model says this pointer must be good and pass to a function, and someone writes code that passes a null pointer to the function, that can be caught at compile time without actually, and save yourself some debugging effort. So ultimately, we have three tests that test the various components. The first test just tests the builder, and in particular the LLM. The second test tests the whole program stat solver and ignores the builder. And the third test puts things all together. So I'll go over each of these in turn. For the first test, we simply construct a manual P model and then ask the LLM to generate a P model for us, and did it get the answer right? For this test, we used the DOS Unix program. That's one of my favorite programs because it's fairly small. It has 169 pointers. It's actually designed to solve a real-world problem, converting new lines between DOS format and Unix format, and vice versa. So I won't claim it's the smallest, but it's one of the smallest bits of open source code that actually does something productive. It was not just written for someone's homework assignment or someone to teach themselves programming. So we kind of hoped that the system would the builder would correctly guess, determine the p-models for all 169, or we were hoping for a 95% accuracy rate. We wound up getting 159 pointers correct, 10 pointers wrong, so that accuracy rate is just a little shy of 95. It's 94.1%, which is close enough. And what we have here is a error breakdown of the 10 pointers that were incorrect. We could easily put effort towards fixing one of these and to get ourselves to the 95%. But that 95% is an arbitrary limit that we set for ourselves. Okay, for the second test, we relied on Juliet. For those who don't know, Juliet is a large test suite released by NIST of about 50,000 small C and C++ programs. They're either good or bad programs. Bad programs violate a particular CWE, and each bad program says, at this line, we're going to violate this CVE. And the good programs are like that, but they don't violate the CVE. So, 50% good, 50% bad. And for our test, we are only concerned with the 5 temporal memory safety CWEs. So, again, we ran just the whole program stat solver, no LLM, no builder. Were these CVEs, or were these programs, were the good programs truly marked as memory safe, and the bad programs marked as memory unsafe? And as you can see in these pie charts, under both good and bad, there were 10% of programs that used features we did not support. There's some features that we haven't, well, note to self, don't ever say that we can't do this, just simply say it's future work. So, for instance, static pointers are future work. In fact, static mutable pointers are even not supported by safe Rust. So that's kind of something that we need to work on. So the 10% that is grayed out here were things that used features that are future work. Of the things that we support, all of the bad examples were recognized as bad by the whole program stat solver, and all but 9% of the good programs were recognized as good, and that 9% works out to 200 programs, and we did an error analysis of these 200 programs. So what we discovered is about half of these programs were cases that we said they are memory safe, but they violate POM. They violate our pointer ownership model, and in those cases, in those cases, I should add that one feature of our model is that it doesn't capture every temporally memory safe C program. It can certainly, there are certainly things you can do in C code that's not POM compliant, such as using reference counting or garbage collection or other more sophisticated memory management techniques. And what Juliet does in a bunch of cases is it takes a pointer that points to the stack, returns that pointer from the function. As you might guess, returning that pointer automatically makes it a zombie, and dereferencing that pointer would be undefined behavior. And in real-world code, you wouldn't return that pointer if you're not going to use it. But Juliet is not real-world code. It's not natural. It's test code, kind of artificial. And Juliet therefore has lots of code examples that return, zombie pointers, but never actually use them. So the code itself is memory safe, but it is not compliant with POM. A third of the examples were cases where the code was memory safe and I guess you could say it complies with POM from a programmer standpoint, but it basically used analysis techniques that foiled static analysis. For example, if you allocate memory using malloc, you're supposed to free it exactly once using free. Freeing it no times is a memory leak. Freeing it 2 or more times is a double free. Well, what if your free function is buried inside a loop, a for loop? Then the static analysis will say, sorry, this loop may execute 0 times or multiple times, not safe, not compliant with POM. Juliet, however, simply has a loop like what you see there, where the loop is designed to run exactly 1 time. So the code is memory safe, but our static analysis didn't recognize that the loop runs exactly once. And trust me, while this code may be memory safe, if you ever submit to me a merge request, a pull request with that kind of loop in it, well, I'm not going to be happy with your code. So on to the third test, where we put things together, the builder, the LLM builder, and the SAT solver. And these were the results we get. The ranges, the LLM produced the correct P models between 72 and 95% of the time. This only occurred, we only did 4,100 of the tests. Those are the ones that did not use unsupported features. So this is the results, and I like to think of this as a glass half full thing. Instead of generating 4,100 P models yourself, the LLM got between 72 and 95% of them correct. When it gets things incorrect, then you'll get an unsat core for a particular function, and you would have to debug that function. So ultimately, if you wanted to get correct P models for all of Juliet, you would just have to fill in the tops of these things until they all reached up to 100%. That's a little bit of work for you, but the LLM has saved you from a lot of work. So speaking of work, future work, again, lots of future work to do. We'd love to do this. This work in time, such as handling arrays of pointers, static pointers. There's a few functions, such as the real path function at POSIX, that simply are, well, they are fancier than what our model can support. Likewise, we did all this work with GPT-04 Mini. There are newer, fancier models out there today that we can work with. To me, we have a sketch of a proof, but making that completely finishing the formal proof is future work. But to me, the most interesting future work is we've just used formal methods and an LLM to work on and partially solve temporal memory safety. Could we use this to do spatial memory safety? Can we identify buffer overflows statically? Could we do concurrency safety? Lots of interesting questions. So I'll give a quick shout out to my team who put this together. Some of them went beyond the call of duty, so they did a great job, great team. And so to conclude, we have a semi-formal model showing memory safety. We can use an LLM to build this model for any program. If the LLM hallucinates, then what we wind up getting is a positive, which might be a false positive. It might say this program that's temporal memory safe really isn't memory safe. It does not ever give you false negatives. It will never say this memory unsafe program really is memory safe. Hallucinations are caught by the SAT solver and produce unsat cores, saying the program is not memory safe. And as you see, the Juliet case correctly recognized all unsafe programs and recognized correctly most of the safe programs. So in conclusion, we have a website available and a GitHub project. The GitHub code was used in the artifact, the reproduction artifact. And finally, last thing is we will be giving a presentation of pointer ownership to the SCI Summer Series happening in Virginia on July, 23rd. So I welcome you all to come over there and listen in on things. Thank you.
Applause. Are there any questions that people have for David? Oh, I should quickly mention that there are 3 of the badges given for this paper. For the previous paper, there was the red and the green badge, and the previous paper was a candidate for the best paper award for the conference. And the next talk, which is going to be given, is also got 2 badges. Well, just a question to David. How do you deal with, you had your irresponsible pointers, and if you did operations on them, change what they're pointing to or dereference them or something, how does your analysis catch that?
So the point of the analysis is to catch lifetimes of irresponsible pointers. So while you can perform arithmetic within an irresponsible pointer, it is important that it not exceed its array. That's a constraint in the C language. You can't hop from this object to that object even if these objects happen to be consecutive in memory, unless they're part of a single larger object. So the main thing is to simply make sure that the irresponsible pointer doesn't outlive whatever it points to.
Okay.
Does that help?
There's a question here.
Great talk. I have one question. So one of the part parts of this is that LLMs do hallucinate. And you found in your code around 94% correctness out of curiosity. Does that change with larger code inputs versus smaller code inputs? Is it more likely to get like the smaller code inputs correct, or does it scale poorly or well?
That's a really good question, and giving a more nuanced answer to that question is future work.
Thank you.
So
Perfect.
DOS Unix is a fairly small bit of program. Juliet is a large test suite of small programs, so we haven't really gotten to answer that question on larger programs yet.
Thank you.
So just something that I don't think you mentioned in your talk, what's the timescale like on solving this model? How long does it actually take to analyze a model, run it through the SAT solver, et cetera?
Very good question. I don't have any of that data down because it always was instantaneous. So SAT solvers, of course, could take a long time if given really huge amounts of code, but we have not managed to give it a large enough code to make it take a long time yet. So future work again.
Thanks, David. Let's give him a round of applause.